All right, first announcement for today. Nothing to do with this class, but if you go to the GCC homepage, on the main page, you will find this link down here, if it doesn't run away, for the 2012 Foundation Scholarships. Is there anybody who got one of these awards last year? Okay, this is a chance for you guys to apply by March the 9th and get some money. There's a whole list of scholarships. You can click on this PDF and you'll see a long list of scholarships that are being offered. Here's the list. I'm just going to show you a couple of them. And here's what I want to say first about this list. First of all, it is quite easy to apply. Generally, you just fill in some basic information about yourself. You write a little essay explaining why you think you should get the award, but it is not an intense process. And I also think that you can apply to several awards with just the same basic application. The other thing that I want to tell you about these awards is that the only people eligible for this money is GCC students. You are not competing with worldwide students, nationwide students, Massachusetts-wide students. You are competing against other GCC students. That's a population of about 2,500 people. I would estimate, this is just a guess, maybe 5% of them are going to apply for one of these awards. 250, so that's 125 students that you are competing with. I'm just throwing a number out there. You will never have a better chance to get some free money than right here, right now. Okay, these awards are going to somebody. Even if one person applies for a particular award, they will get that award. Just showing you a couple of examples. The 25th Anniversary Scholarship, there is one of those awards for $825. I don't know about you, but to me that feels like real money. Is given to somebody based on the basis of scholarship, financial need, and character. And what you'll need is a recommendation letter from a faculty member or a clergy person. I'm going to scroll down a little bit to this bottom one here. Here is a scholarship worth $550 given to a female student to help her make a transition to academic life. Okay, so we just eliminated half of the people who might apply for that. So half of you are thrilled and half of you are not so happy. But I want to just show you that it's not even just all GCC. Like some of these are kind of narrower and narrower, and I guarantee you a lot of you fit into a lot of these categories. I'll show you one more. This guy right here, another $850 for this one, an outstanding student in business or a business-related major. Just imagine, how many business majors do we have here? How many of them are going to apply for this award? Like, there's some good odds if you put your name in the hat. So just putting it out there, it's on the main page, lots of information there, and I think it's a fairly easy process to apply for these awards. Any questions about any of this? I don't think there's one for each major. I think that which majors are selected are a function of like the people that donate the money. So this person presumably had some affiliation with the business department, so they have an award for her now. Any other questions? Okay. All right, next thing is, let's go back here. So if you guys go to, if you log into Moodle, and there's instructions on the syllabus if you've never done that before, this is what our page looks like. It's breathtaking, isn't it? It's just lovely. But the very first thing here says how to access class videos. This is new because we didn't have class videos before, but we've got them now. And if you open that document, you will see this document. And it says if you want to watch the video from February the 3rd, you go to this link. And so I'm just gonna, if you mouse over, it says like control click to follow the link, so you can do that, or you can copy and paste the link. And if your computer is set up just so, then some media player will open up. I'm going to fast forward a little bit, and I'm going to turn the sound on. Okay, and like so, I mean, like you can see that, well, you couldn't see it, but as I write, this thing gets written on. And so everything that happens on the smartboard and everything that I say is captured in real time, and you make this video. And I think it's a nice resource. So check it out. Yeah, Topher. Yes, it's kind of like that. It's like that scene in Spaceballs where they want to know what's going to happen, and so then they take the Spaceballs movie out of the rack and they watch. Yes. Yeah, it's because we got the Up here, so there's this recording thing, which is current, and then there's the other one up here, which is from the video. That's okay. All right. Okay, so so that is that. I think that is all good. Yeah, I'm kind of confused as to which ones are. All right. So that's that. And here's the deal. The way in which, if you had me last semester, I posted the videos on Blackboard. I have been discouraged from posting the videos on Moodle. They're quite large. I don't know if you noticed, this is a website. You can access this website from anywhere. It doesn't have to be on campus. This is a streaming server that the video is now put on. So go to that website from anywhere in the world and the video will stream to your computer. The nice thing here, I'm not going to make a document like this for every single class. This is the form that the websites will have. So today's video will look exactly like this, but instead of 03, it becomes 08, okay? So whatever date you're interested in, just type in the right date and the video should pop up. Now, today's only the second video. There should be one from the 6th, but I had some technical issues, so there isn't one for that, but that's the website. Any questions? All right. So we're on page 28. The calendar is here. Project number 2, I'm hoping you guys have been working on it. It's due on, what is that, Monday? February the 13th? Okay, in terms of project 2, it is a challenging project, and if you don't have a good technique, you can go through some very tedious and painful calculations to try to answer these questions, and that's not the goal. So I'm open to talking to folks individually or in little groups about the project. So if you've made some progress but you want to kind of check in, then do so. Find me here or in my office or in the studio. And maybe on Friday, I don't know, I have to decide how I can best convey some information, because I think that maybe some of us don't have the tools, you know, like the calculator can do some things that will help you on this project, but I'm guessing that a lot of us don't know that yet. And so on the project, I referenced a couple of commands, the sequence command and the sum command, but I'm guessing that most of us have never used those before. I don't know, we'll figure something out. But like I said when I handed the project out, I encourage you to not wait until the thing is due, but rather you know, really get started on it early if possible. Chris? I think I'll have them on Friday. Yeah. Okay. And then next class, what else do we have? We have our second quiz, and I think that quiz is also no calculator, but it's going to be on everything from classes 4, 5, and 6. Okay. Any questions on that? All right. So we are on page 28 of the packet. And last class, we actually ended up kind of jumping ahead a little bit and getting a jump start on this material. And we introduced the idea of logarithm, although I think that everybody in this room had already seen logarithms. So we're going to try number 6, and it starts with this kind of funny acronym CVQ, which I don't have a whole lot of these throughout the notes, but it stands for Classroom Voting Question. So it's a multiple choice, and you guys are going to come up with some answer in your table and then vote. So let's get a reader for this one. Can we go to Richard, number 6? Okay, try your hands at that one. Again, calculators away. I think that this is a challenging question, but working your way through this, I'm hoping, kind of solidified what does it really mean to talk about a logarithm. It's just kind of a formula, and the first version of this formula that a lot of folks talked about was 8 raised to the 0 equals blah. And that's all that a logarithm is. It's always that pattern of things. So 16 is the right answer. Well done. Let's go down to number 7, and we'll go to Kate. Okay, let's see if we can fill in some of these properties. Log of 1, 10 raised to the something is supposed to equal 1, it's 0. ln of 1, 0 for the same reason. Log of 10 is 1, ln of e is 1. Log of 10 to the x is x. So we see those two things, we just cancel. You just get the power. Same thing on the right-hand side. Okay, then we get to some properties that maybe you know, in some previous class, you guys did some examples where you use this property. I don't think this is a particularly useful property of logs today. back in the day before we had calculators, this was a very useful property, but what just happened? What happened? Where what page are you guys on? Undo, undo, undo. We'll make use. Undo. That's the right page. Okay. Yeah, so apparently there's some very nice, easy to perform gesture that deletes several pages. Oh, I think I might have accidentally hit it with my pants or something. That delete key. Okay. Log of A plus log of B. All right, so products become sums inside of logs. Same thing over here. So if products become sums, then quotients become subtractions, differences. Log A minus log B, top minus bottom. All right, for me, the most useful property in this list is F. What can you do when you have a power inside of a log? And bring it down into the front. This is why I care about logs. P ln of x. Power comes down in the front. You don't need to write it, but I'll put a little dot there just to indicate it is multiplication. And then G is quite funny looking, but 10 to the log x. Is it log x? It's just x. Thank you. Turns out that the 10 and log, they're inverse functions. And actually part C is one version of saying that they're inverse functions. And part G is the other direction of saying they're inverse functions. E to the ln of x is just x. You see E and ln next to each other, either in the top version or the bottom version, they cancel and you just get the x. All right, so if we've got all the properties, we go to the next page, and I think we're up to Tacit. Go ahead. Okay, so let's try this one. The most important word in this question, continuous. That is the most important word. So that means that we're using our PERT formula. So, I mean, you can change the letters if you want. I think the book uses, I don't know, E to the K, something. Doesn't matter to me what letters you use. I'll just call it PERT because ACT is harder to say. And we start filling in. What is the principal? 40,000. E to the rate, 013, and then T is the thing we're after. And A is the future amount of, which is 50,000. All right, and the goal is to solve for T, and the T is in the exponent. And to date in this class, the only way we've been able to solve equations where the variable is in the exponent is by graphing and intersecting two things. But now that we have logs, we don't need to do that anymore. So first thing to do before we take logs is what? Is divide by that 40,000. You got to get the exponential thing by itself first. So we divide by 40,000, cancel all those zeros and get 5/4 is e to the 0.013t. I'm going to write that over here again with a little bit of space. E to the, and the idea here is that if you have a variable up in the power, you use logs to get it down. So you could use log, like the common log, but better would be ln, the natural log, because that's the thing that's going to cancel with the e. So I wrote it again just so I could Say, okay, we're just doing the same thing to both sides, and that's hitting it with an ln, taking the natural log of both sides. You're welcome to type in ln of 5/4 right now, but I think if you do, and then you just retype that number, you're introducing rounding error where we don't need to, so I'm just going to hold off on using the calculator until the end. But one thing that's nice here is that the right-hand side, I see ln and I see e, and they cancel each other. So what's the only thing remaining on the right-hand side? Is this 0.013t. That's why we used ln, so that it would right away cancel with that e. And the last step to solve for t is to divide. ln of 5/4, all divided by 0.013. Okay, and so we'll just type that in and we'll get our answer. ln of 5/4 divided by 0.013. 17.16 what? Years. This is how long. And logs are useful to answer any kind of question involving how long. Questions on that one? Okay, and if instead of, we'll answer the second one here, instead of doing continuous, we had done compounded annually, but we can just change the formula, right? It's not PERT anymore. It's the other one, P1 plus R over N to the NT. If we're compounding annually, how much is N? Is 1, once a year. So in fact, oftentimes you don't even bother with that. You just call it 1 plus R to the T, once a year for both of those N's. And so we'll fill in all the blanks. How much is the A? The A is the 50, the future. And then we've got the P is still, oops, is still 40. And then we have 1 plus the R, 0.013, to the T. Yeah, and that's probably what we would do in the very first step is divide by 40,000, and then you get exactly 5 and 4. Okay, so I think I need a little more space, so I'm going to grab a little more space. So if you divide both sides, you get this. And then what do we do? Because the variable is upstairs, take log. Do you want to use ln or do you want to use regular log? Doesn't matter. Whatever you want. In the previous one, ln was the natural choice. Get it? The natural choice. Thank you. Thank you. You have to laugh louder if it's going to get picked up by the microphone. But here, either way is fine. So let's just use log just so we have practice with that other button. So log of both sides, log 5/4 equals log 1.013 to the T. And so things don't work out quite as nicely as they did in the previous question, because you can't just cross off the log and the 1.013. They don't cancel in the way that ln and e canceled before. But what can you do when you have a variable inside of your log? Yeah, bring it right down to the front. T times the log of 1.013. That's the property. That's the one that I said is the most useful. And then finally solving for t, well, log of 1.013 is just some number. We divide both sides by it. So we get t is log of 5/4 divided by the log of 1.013. That's yeah, that's a really nice way to see it. This is just an example of the change of base formula. If you did ln's instead of logs, it would look exactly the same, and you'll get the same answer. Before we type it in, can I ask you guys to think for just a moment? Do you expect that this answer is more or less than 17 years? 17 is what we got for 17.16 was what we got. Talk to your neighbors. Talk to your neighbors. See if you can agree. Okay, so do we think more or less time? It'll take a little bit more time because you don't get the people as fast as you were before. So to get to 50,000 will take a little longer than the 17.16 years. When we type it in, maybe type it in, and we get 17.27 years, a little bit longer. Questions on this one? Okay, so let's try the next one. We'll go to number 9, and I think we're up to Emily. Okay, so let's try part A first. 15e to the 0.2t is 20e to the 0.01t. Do you think you guys could come up with with a question where solving this equation will answer your question? You guys talk to your neighbors. Can you come up with a question where you would want to solve this equation to answer your question? So I think some different groups kind of saw this as being about money. And the one guy has $15 invested at 2%, that's PERT. And the other person has $20 invested at 1%. And at some point, the $15 person will catch the $20 person. So how long will it take until they have the same amount of money? Let's solve this question to find out. So the idea here is to get the e's on the same side. You could subtract. I'm going to divide both sides by the smaller e. So divide both sides by 15, divide both sides by e to the 0.01t. So I got 15. What do we do with these powers when we have them on top of each other like that? We subtract, right? We know when we have the same base, you subtract the powers. So when we subtract, we get e to the 0.01t. And that's equal to 20. Yeah? Keep the base, subtract the powers. And then divide both sides by 15. And then take what of both sides? Natural log. Excellent. So I'm just going to kind of skip the one step and say, well, what do you get when you take the ln of the left? 0.01t, and that's equal to ln of the right, 4/3. And then divide. ln of 4/3 divide by 0.01. Yeah, if you use ln because there was an e, then you're right. You don't end up with that log on the bottom. So what did we end up saying here? ln of 4, what was it? ln of 4/5? 4/3. Divide by 0.01. So almost 29 years is how long it would take for the one person to catch the other person. Questions on this one? Todd? No, that's fine. Okay, part B, another equation where the variable is in the exponent. We got t's up there. This one is quite difficult, actually. And when like I looked at this problem, I put it in the notes a while back, and then I looked at it more recently. And at first I was dumbfounded because I didn't know what to do. What do I do? What makes this one harder than the previous one? Yeah, it's not the same base. That's it. We had e's for both. So when you divided these e's together, they combined quite nicely. And you just had this e to the 0.01. But here the bases are different. 1.01 and 1.06, there's no nice rule to merge them together. So it's actually a different thing that's going to save us here. This is a little bit tricky. First thing I'm going to do, I'll divide both sides by 100. At least we can do that. And then we're going to get these t things over to the same side. So let's try that, 1.01. So we'll divide both sides by the 1.06 to the t. So we get this, 1.01 to the 12t divide 1.06 to the t. And that's equal to 2. So far, this is the same process as before. You get all the t's on one side and the numbers on the other side. But the difficulty here is we can't just merge these together like we did before. So here's the twist. Is this the same or different from what it was without those brackets? One vote for the same. If I gave you this problem with brackets, what would you do with the powers? You multiply them, which is exactly what we had, right? So it's the same. But the nice thing is that this 1.01 to the 12 is some number, whatever it is. But now the thing on the top and the thing on the bottom are both raised to what power? They're both raised to the t. That's how we get the sameness. That's how we get a property that we can use. And I'll write it over here just to kind of remind us. If you have something like a over b to the t, you guys agree that's the same as a to the t over b to the t? This is a property we've seen. We're going the other direction. You have two things both raised to the t. You can merge it together and make one fraction raised to the t. So let's do it. So we get 1.01 to the 12, divide by 1.06, whole thing to the t. Very sneaky. Other questions on what made that work? Yeah, you can type it in now if you want. I'm going to type it in once at the end. But what do we do to both sides? Because the variable is up here, we use logs. Okay, so let's use ln. You could use the other one if you want. ln of 1.01 to the 12 divided by 1.06 t equals ln of 2. And what can you do with that t? Bring it down. And then divide. Both sides by that big old ln on the left-hand side. Okay, I'm tired of writing. I'm sure you are too. I'm just going to type it into the calculator. 11.33. Yeah, so it's not a bad thing to use extra parentheses to really make sure you're grouping things correctly. The calculator follows order of operations. So which one does it do here? Does it do the 12th power, or does it do the divide by first? Does that power first, which is exactly what I wanted to do. Okay, so we'll say about 11.34 is our answer. Okay, that one is substantially harder than the one up above. Any questions on that one? Okay, and the next one is going to be like a breath of fresh air compared to that one. Log of 3x plus 4 equals 3. Sometimes people do funny things when they're faced with equations like this, but it's quite easy if you just kind of follow the pattern that tells you how to go from this to the exponential version of this. What's the base? 10. So the exponential version of this says 10 raised to the third equals 3x plus 4. Right? Just follow the pattern. This is a really easy equation to solve. I got 332. Questions on that one? Okay, we'll go to number 10 for Sam. Thank you. Todd? Okay, so astronomers have to deal with very large numbers, and that's not too terrible today with calculators and computers. But before we had these wonderful devices, astronomers spent quite a bit of time doing long multiplication problems because they had no alternative to that. And so this invention of logs, like if you just, I'm not going to get into how logs really kind of helped, but for example, is the log of this, all right, so 145,000 is a pretty big number. How about the log of that? Can you hold up the number of fingers that is roughly the log of that? Is that equal to 2, 3, 4, 18 million? Right? Yeah, I mean, like it's 10 raised to some power. Well, if this was 100,000, that would be 10 to the fifth. Well, this is more than that, but it's less than a million. This is between 5 and 6. And so logs have the effect of taking very large numbers and scaling them down quite dramatically. 145,000 became 5. So what they would do, these astronomers, they'd say, okay, well, I need to multiply this times this, right? Let's, oh my gosh. So okay, so suppose they had to do this long. Imagine sitting down and like it doesn't look terrible because I could just hit enter and it will tell me. But that's because you guys are spoiled by the fact that you have this thing you can just hit enter. But could you imagine having to do this multiplication? I don't know how long that would take. 10 minutes? 20 minutes? And how accurate? Like you got to make sure you get it right. You make any mistake in this long multiplication, it's all over. Okay, so instead of doing that, they'd say, okay, how about instead of doing that, we think about taking second insert, the log of that. Now that's no better if you still have to multiply them, but you have a property that says if you want to take the log of two things multiplied, you can split it up into two logs. Multiplication becomes what? Addition. So really, this question is the same as the log of this thing, so I can insert, log of this thing plus the log of that thing. Getting rid of the times. Delete. This is the same as what it was before. That's our property. Log of a product becomes a sum of logs. Okay, so the log of 14,586, you guys just held up the number of fingers. You said, well, it's about 5 or 6. And we want more accuracy, obviously. Well, there are little tables that you can use that tell you how to figure out the log of 14,586 a little more accurately than just saying it's about 5. Lots of laborious calculations. Like really, really, lots of. They used to have the tables. Yes. So back in not too long ago, 30 years ago, if you look in the algebra, look at the back of an algebra book, you will see these very detailed log tables. So you take one of those tables out, you figure out the log of 14,586, you add the log of the other number, and that's almost the answer. We didn't really want this. We wanted this without the log. I took the log of something. I need to undo it at the end. Whatever you get, take 10, raise it to that power, and that'll be the answer. It sounds more involved than it is, especially compared to the long multiplication that we were really after from the beginning. And so Laplace said that Napier's invention doubled the life of the astronomer. The astronomer spent half of their career doing arithmetic. But then this guy comes along and invents these logarithms and doubles the productive life of the astronomer. This is not why logs are useful now because we've got the calculators, but this really helped a lot of folks like these guys. Okay, let's go to the next sentence for Steve. Let's pause right there. Could you read it again?
There you go.
Right. So this was not a free thing. There was not just a place on eBay you go and say, give me the log table. Right? 20 years of laborious calculations to make the first ever log table. And then astronomers were able to use it. Go ahead, Steve. Okay, so let's spend, what do we have? 23 minutes? Let's see if we could spend about half of that and tell me how far you guys might be able to get on these 4 problems. Very rarely will I ask that you use the textbook, so don't feel like you need to bring it every day, but I'm sure somebody at each table has it, so see how far you can get on these, and then maybe we'll start next class.